Welcome back to our series on statistical methods. I'm Mark Ledbetter, and we are in the ANOVA and Design of Experiments section of the course. This is Lecture 2, Part 2, and last time we covered Chapter 1, and so we talked about how we describe sample data and defined random samples. We talked about different statistics such as the mean, the variance, standard deviation, and many others that we might calculate. We talked about the fact that sample values are statistics that are used to estimate population parameters, which we don't know. So population parameters would be the population mean, population variance, and population standard deviation. And then we talked about how we estimate parameters. We also discussed and showed some descriptive statistics, which is one of the first steps we should do in statistical analysis. Specifically in R, we talked about the favstats function from the Mosaic package, and it calculates these quantities here. We also discussed the describe by function from the psych package. It calculates everything except for Q1 and Q3 from above, and then it adds on skewness, kurtosis, and the trimmed mean, and the standard error of the standard error as well. So then we talked about visually representing the data, and we talked about the histogram or hist function from R, and these were all in the basic graphics package that comes with R, so there's no loading of libraries or packages to get these. So we did the histogram function, and I gave you code so that you could create your own histogram, the dot plot function, and the box plot function for comparing, in this case, two different formulations of some cement or mortar. In order to do some of these calculations, it was nice to be able to use the melt function in the reshape2 package to basically stack the columns of data on top of each other. So we had data that had the modified data here, and we had the unmodified data here, and these were tension bond strengths in kilogram force per centimeter squared. And we were able to, using the melt function, just stack these into one, or combine them and stack them into one variable, and then the actual descriptors or column titles were used as the variable, or we called it level treatment. I think I called the variable the treatment, so it might say modified, modified, and then unmodified, and then we'd have our strength here, and we had the individual strength variables, and then we were able to use the box plots, dot plots, and histogram functions much easier. So we're going to continue in Chapter 2, and let's get started. When we talk about evaluating estimators, we want to talk, so an estimate is a sample statistic, but we're talking about the form of it or formula of it now in more of an theoretical consideration right now. So if I have some parameter theta, then its estimate would be called theta hat. We put a hat on there to represent that it's not the parameter but an estimate of the parameter. It's calculated usually from the sample data. Okay, so the first concept is bias. So this is the statistical bias, and the statistical bias of an estimator, theta hat, is calculated as the expected value of theta hat minus theta, the parameter it is estimating. So one easy example for us to do, because we know these values, is we know the expected value of x bar, and x bar is an estimator for mu. Oops. And so we could say that this is equal to mu hat. Okay, and so wherever we have theta hat, we are going to substitute in x bar. And so we have E of x bar, and we know that that is equal to mu. So the bias of x bar is equal to E of x bar minus mu, the parameter it's estimating. And so we plug in for E of x bar, we get mu minus mu, we get 0, and that means that x bar is an unbiased estimator of mu. Now, one of the most widely used criteria for determining how good an estimator is called the mean squared error, or MSE, of theta hat. And the definition would look familiar to you. It might look like the variance, and we're going to see how it's related to the variance. And so E of theta hat minus theta squared can be written as the variance of theta hat plus the bias of theta hat quantity squared. Don't forget the square here. And so for x bar, I forgot to square this. For x bar, the MSE is variance of x bar plus the bias of x bar quantity squared, but we showed that the bias was 0, so this term goes to 0, and we're left with the MSE for x bar reduces to the variance of x bar, and we know that as well. It is sigma squared over n. I want to remind you that x bar and s squared are both unbiased estimators of mu and sigma squared, respectively. However, the sample standard deviation is not an unbiased estimator of sigma. It is still one of the best estimators, but it is not unbiased. It is slightly biased. So let's do the derivation of the MSE. We're going to start off with the definition. E of theta hat minus theta quantity squared. Now the first thing we're going to do is expand this square. So we end up with E of theta hat squared minus 2 theta hat theta plus theta squared. We're going to distribute the linear operator, the expected value, and we end up with E of theta hat squared minus 2 theta E of theta hat plus E of theta is simply E of theta squared is simply theta squared. Okay, and then we can because theta is a constant, so then we can rewrite this as E of theta hat squared and then minus E of theta hat quantity squared plus E of theta hat quantity squared. So I've just added and subtracted the same value. That puts it as net of 0. And then minus 2 theta E of theta hat plus theta squared. Now our definition of variance of theta hat would be given by this expression right here. So I take the expected value of something minus the square of its expected value. So I take the expected value of the square of something minus the square of the expected value. That is the variance of our quantity. So this is V of theta hat. And now I have a perfect square here. So this can be rewritten as plus E of theta hat minus theta quantity squared. And this is theta hat, variance of theta hat, plus the bias of theta hat quantity squared. And so we have derived that. A fairly simple derivation if you know the trick of adding and subtracting, what to add and subtract in there to complete the variance and then make it a perfect square as well. All right. So the degrees of freedom of a sum of squares, so something that you might see SS is our abbreviation for the sum of squares, it's the number of independent elements in that sum of squares. So here's an example. We have the expected value of yi minus y bar quantity squared. And so I is equal to 1, 2, up to n. So there are n quantities here. And so I am going to So I actually wrote this wrong. This is supposed to be a summation. All right, so I apologize for that. So we have the sum of yi minus y bar squared. And so for this, we have the first term, y1 minus y bar, then the second term, y2 minus y bar, and so forth until we get to yn minus y bar. Now, if we add these up, we have y1 plus y2 plus ... yn. So the sum of these is going to be the sum of yi, which is what we have here. And then I have n of these terms as well, and so I have bar, minus, and there's n of these. So if I factor out the negative, I'd have y bar plus y bar plus y bar, and there's n of these. So that's n times y bar, which is what I have here. Now, if I multiply out n times y bar, then I get something simple. I get n times y bar is equal to n times 1 over n sum of yi. These cancel. I'm left with the sum of yi. Now this is equal to 0. Okay. So I can't, by adding all these up, I can't say that since they're equal to 0 in this case, they're not all independent. Only n minus 1 of these terms are independent of each other. So in other words, if we have any n minus 1 of the values and we have y bar, we can figure out the missing value using the equation of y bar. Okay? So the degrees of freedom is n minus 1 in this case. All right? So, all right. Now, in general, if a sum of squares has nu, this is the Greek letter nu, degrees of freedom, then the expected value of that sum of squares divided by its degrees of freedom is equal to sigma squared. All right? This is in general. And this is a good thing to know, so I would certainly put this somewhere on your formula sheet, whether you put it within transformations or whether you put it with just a blank formula sheet. I don't know where you need to put it so that you can find it, okay? So personally, I would put it on the sheet with my transformations and make a special box for it and star it so that my eyes are drawn to that when I look. Okay, so here are some of the important transformations that you need to know in this class to make your life easier when you're doing derivations. So first, if Z1, Z2, up to Zn are IID, that means independent and identically distributed, so they all have the same standard normal distribution. Then if we set x equal to the sum of the squares of these, so x is equal to the sum of zi squared, that has a chi-squared distribution with degrees of freedom n. Why? Because if z is a standard normal distribution, then z squared has a chi-squared with 1. And then if we sum chi-squared distributions, then we add up their degrees of freedom. So there's 1 here, up to 1 here. And so there's n of those. That makes the degrees of freedom n. Okay? Now, if y1, y2, up to yn are IID normal with the mean mu and variance sigma squared, then we take the sum of squares divided by sigma squared. This has an n minus 1 chi-squared with n minus 1 degrees of freedom. All right? So this is something else that we showed. If z is a standard normal and it is independent of u, which is a chi-squared with n degrees of freedom, then t, which is equal to z divided by the square root of u over n, remember, n's its degree of freedom, this has a t distribution with n minus 1 degrees of freedom. So this is our t statistic. Okay? So this is a transformation from normal and chi-squared to get a t statistic. So again, these things are really important to know. I hope you have them on a sheet where you can find them easily. Now, number 5, if u is a chi-squared with n1 degrees of freedom, and that's independent of v, which is a chi-squared with n2 degrees of freedom, Then we take the ratio U divided by its degrees of freedom divided by V divided by its degrees of freedom. Then we get the F distribution with N1 degrees of freedom in the numerator, N2 degrees of freedom in the denominator. That's why I write it like this, even though I could simplify it. It's easier to see that on the top, in the numerator, I have N1 degrees of freedom, and in the denominator, I have N2 degrees of freedom when it's written this way. Okay? If you simplify that fraction, then it may become confusing because you'll end up with N1 on the bottom and N2 on the top, which is reversed. So be careful with that. 6, if we have two independent normally distributed populations with common variances, so sigma 1 squared equals sigma 2 squared, and we can just call that, we can just simply call that sigma squared since they're equal. And they have sample standard deviations S1 and S2, S1, S2. Then the ratio S1 squared over S2 squared has a F distribution with N1 minus 1 degrees of freedom in the numerator, N2 minus 1 degrees of freedom in the denominator. Okay, so this is because we can write S1 squared as the sum of Y1I minus Y1 bar squared. So this 1 is this 1, okay? And I probably should use J, but I didn't. I used I. So 1I minus Y bar of 1, okay? Then we could rewrite the top as SS1 over N minus 1 on the bottom. And if you remember, so then we have that SS1 divided by sigma 1 squared is equal to SS2 divided by sigma 2, or I'm sorry, it's SS1 divided by sigma squared, because this stays the same, and this can be rewritten as just sigma squared, the common variance. This will have a chi-squared with N1 minus 1 degrees of freedom. Okay? So, S2 squared then has, that can be written sum of Y2I minus Y2 bar squared over N2 minus 1, or I could write that as SS2 over N2 minus 1, and then we know that SS2 over sigma 2 squared is the same as SS2 over sigma squared, and it also has a chi-squared distribution, but now with N2 minus 1 degrees of freedom. So I can rewrite S1 squared over S2 squared here as S1 squared over sigma squared over S2 squared over sigma squared, right? So these would cancel out, so that's how we get this. And so this is going to be a chi-squared N1 minus 1 degrees of freedom over a chi-squared N2 minus 1 degrees of freedom, which gives me an F distribution with N1 minus 1 in the numerator, N2 minus 1 degrees of freedom in the denominator. And so that is how we show that, using what we've shown up here previously with our transformations. Okay, so looks like I didn't need this page. So let's talk about hypothesis testing. So statistical hypothesis testing is a very useful framework in many of the experimental situations, especially in this class. We'll use it a lot. But in the practice of statistics, it's very common to use hypothesis testing. Some people use it without realizing that they're actually doing it. I don't want you to be in that arena. I want you to really understand what you're doing when you're practicing statistics. So the methodology was developed in the early 1900s, so it's been around for quite a while now, over 100 years. we're going to use a procedure in this chapter known as the two-sample t-test. Before we do that, I want to talk about hypothesis tests in general. So it is very important that you follow this structure when you are doing hypothesis tests. I hope you'll do it in your practice in real life, but you certainly need to do it in this class. Get in the habit of it. This will make you, this will show that you are a professional when it comes to statistics when you're practicing, okay? So the first step is a hypothesis statement. Then we do the test statistic. Then we'll do the critical region or rejection criteria or rejection region. Those are all names for the same thing, but the technical term is the critical region. Then we will have a decision, which is not really the conclusion, although many books muddle this up. The conclusion is a statement that we write that interprets what we found for the lay person, so someone who does not have good training or high level of training in statistics. Okay, so this statement translates everything you've done into common English, where anyone who reads it should have a good idea of what has happened, of what you have found in your test. Okay, but before we do a hypothesis test, especially in this class, with the topics we're going to be discussing, you need a model. Okay, so we need a model, and it's going to be one of the first things you write when you write your hypothesis statement. You need to include a model in it. Okay, so Yij equals mu I plus epsilon ij. Mu I is the mean of the ith treatment level or factor level. Okay, and J is the observation. These are the observations. Now, I've put n sub I, so in the different treatment levels, you could have unequal or uneven number of observations. This makes the analysis more complicated, but it can be done. We're not going to focus on that too much. We're going to stick with the balance case, but it does happen that you, in real life, that you run into these situations where you can't help but have an unbalanced design or unequal sample sizes. So Yij is the jth observation from the factor level I. Here we only have one treatment, and we have two levels within that, two factor levels within that one input variable, if you will. And then mu of I is the mean response. So the response is Y. That's our output. And so it's the mean response, so the mean value of Y for the ith factor level overall. So you're averaging all of the outcomes in the ith factor level. That's mu sub I. And then epsilon ij is the random error associated with each observation, the ijth observation. So epsilon ij is a random variable, and it has a distribution, and the assumptions that we'll use in this section and that we need to test are that epsilon ij is normally independently, this I stands for independently, distributed. So it has a normally identically distributed or independently distributed with mean 0 in this case and variance sigma sub I squared. This implies that Yij has a normal independent distribution mu I and sigma I squared. How? Well, if we take E of Yij, that's going to be E of mu ij, mu I, not ij, mu I. There's no j with mu. Let me make this smaller. E of mu I, which is a constant, plus E of epsilon ij, which is going to equal mu I plus the expected value of epsilon ij. The mean is the expected value, So that is 0, and so that is mu I. That is going to be the mean of yij is going to be mu I. And then the variance of yij is equal to the variance of mu I plus epsilon ij. So mu I is a constant, okay? And so this is just simply going to be the variance of epsilon ij, and this is equal to sigma I squared, because this is a constant. And so when we apply our covariance rules for variance, remember, when we have the variance of mu I plus epsilon ij is equal to the covariance of mu I plus epsilon ij with itself, mu I plus epsilon ij. And we have to take all four terms, we match those two up, then we match these two up, then we match these two, and we add them. And so anything that has the covariance of a constant with a random variable is 0. So we lose all the mu's. And the only thing that we have left is the epsilon and the epsilon. So that's the variance of epsilon ij. And we've said that the variance of epsilon ij is here. And since epsilon is normal, then when we take a constant plus a normal random variable, we get a normal random variable back. So that is why we can show and assume that y has a normal distribution. Okay, y has a normal distribution with mean mu sub I, so yij, mean mu sub I, variance sigma I squared. We also need to choose a type 1 error level for our experiment, and the type 1 error is alpha. So alpha is our type 1 error, and the probability that we have a type 1 error is the probability that we reject H naught, the null hypothesis, given that it is true. Now we're going to use, so H naught is used for our baseline, to determine our baseline probability. Our probabilities are based off H naught being true, okay? And then we're going to check to see how likely it is that the sample that we have occurred under H naught being true. So this is called our significance level. It's a type 1 error. It's the probability that we reject H naught when we should not. So it's making an error that's saying that H1 is true when it's really not. Okay? And then beta is our type 2 error. And the probability that we have a type 2 error is equal to the probability that we fail to reject H naught. So we don't reject it when it's actually not true. Okay, so that's another error. That's a different type of error. Now, 1 minus alpha is our coverage probability. And so that is the probability that if we have an interval, that the interval covers the true parameter value. That's one way of thinking about it. Okay? And then 1 minus beta is the power of the test. So that's going to be the probability that we reject H naught given H naught is false. So the power of the test, how well we, or how good we are at identifying that the null hypothesis is not true in favor of the alternative, or one of the alternatives. Okay. So this nice table gives you the relationships between these quantities. So with hypothesis testing, we're going to do something called this two-sample t-test. We're going to start out with some more idealistic cases. So with our Portland cement example, remember that mu1, this was the modified. So they added the latex emulsion chemical to the mixture, and it reduced the cure time. But these are the tension bond strength levels, that's what we were concerned, that it might have lowered that or made it worse. And so this was the original or unmodified formulation of the mortar. Okay? And so we're assuming that they're both normally distributed, and that the mean of the unmodified is mu2 and its variance is sigma 2 squared. Similarly, we have for the modified that mu1 is the mean of the tension bond strength, and so we also have variance sigma 1 squared. Okay? So this is for factor level 1. And so I'll zoom in so you can see that we have y11, y22, or 1, 2, on up to y1, n minus 1. That's supposed to be an n minus 1 there. Okay, hard to get these typesetting programs to adequately display these things in some cases. So that's the notation there. And then for under the second sample, we'd have y21, y22 up to y. I'm sorry, that wasn't n minus 1, that was n1, so that was right, okay. So n minus 1 would be here, y1, comma, n1 minus 1. And so this is y1, n1, the n1th, the last observation in the modified group. And this would be y2, n2, so the n2th or last observation in the unmodified group. Okay? So that's our sampling situation. Now, the hypothesis test, or hypothesis statement. So we can write the hypothesis statement one of two ways for this test. We can write h naught mu1 is equal to mu2, okay, versus h1 mu1 is not equal to mu2. And we could say, add to this, for the model, Yij is equal to mu1 plus epsilon ij, I equals 1 to 2, j equals 1 to n I. Okay? And then at alpha equals 0.05. So this is what you should say. All of this should be in your hypothesis statement. Okay? So you need to communicate all of this information in the hypothesis statement. Okay? Now another way to write this is we could subtract mu2 from both sides, and we could use 0 over here, which is what we have now. But we don't have to use 0. We could use some null value. So mu1 minus mu2 is equal to 2 or something. We can say there is a difference. We're thinking that it's equal to about 1, let's say. So we could change this to 1, and then this would have to be 1. So they have to be the same numbers on both sides. But in our case, in most of the cases, we're going to be looking to see, so the equivalent of this would be 0. Oops. Okay, so this, putting 0 here makes these two statements and these two statements the same. Okay, but we could test for some value besides 0 here. Okay, that is possible. Now, I've asked this question. This is a very important thing to keep into mind, because there will come a time when we're doing a hypothesis test, or we're testing for data to be normally distributed, and we're going to abuse our hypothesis test. Okay? And so I want you to be aware that we're abusing it. So be careful with the null hypothesis. We never believe that the null hypothesis is true when it's written this way, is with an equal sign. Because what's the probability that H naught is true? What we're saying is that mu1 is the mean of treatment level 1. So the probability that X bar is equal to mu1 is a similar statement to this. And then the probability that x bar 1, x bar 2 is equal to mu2. And so if we have an equal sign, then this probability is going to be 0. This probability is going to be 0. If we add them, we get 0. So when we have an equal sign in the null hypothesis, when it's written this way, the probability that the null hypothesis is true is actually 0. Okay? So if it's 0, then there's no way that we're going to say that we believe the null hypothesis. Okay? All right. Now, when we get to advanced inference in higher level courses, we'll talk about alternate ways to write the null hypothesis in such a way that it has a positive probability. But in this method, there is no probability associated with the, there's 0 probability that the null hypothesis is actually true. Okay, so parameter estimates. Remember, y bar is the sum of the yi's divided by n. So for each, this is an estimation of mu, but if we wanted y1 bar, that's going to be 1 over n1, sum of y1, we'll call it j equals 1 to n1. Okay, so there's another way of writing the mean. And then s squared is equal to 1 over n minus 1, sum of yi minus y bar squared. Now, s1 squared is equal to 1 over n1, sum from j equals 1 to n1, y1j minus y1 bar quantity squared. Okay, so we'll need to know how to calculate these quantities. So I hope that you're able to see what we're doing with the indices here. So how does the two-sample t-test work? Well, it uses sample means to make inferences about our population means. So what we're going to do is we're going to take the difference in the sample means and divide it by the standard deviation of the difference in sample means. This is the standard error of x bar 1 minus x bar 2. Okay? All right. So we can have sigma of y bar squared is, remember, the variance of y bar is sigma squared divided by n. And so if we take the variance of y1 bar minus y2 bar, okay, and y1 and y2 bars are independent, then this is going to be the variance of y1 bar plus the variance of y2 bar, because the covariances are equal to 0, and this is the same as the variance of y1 bar plus the negative y2 bar. And so we could write this as the variance of y1 bar plus the variance of negative y2 bar, and this negative 1 comes out twice because it's a variance. We square it, and so we end up with the variance of y1 bar plus the variance, plus the variance of y2 bar. Okay? And so y1 bar, that variance is here. y2 bar, that variance is here. So this says that if we want our test statistic, we would take y1 bar minus y2 bar over the square root of our variance, which is now given here. Okay? So now, this is a big if. If we actually know the variances, we can use the normal distribution. And we could say that Z naught here, our test statistic, that's what this is called, our test statistic, would have a standard normal distribution as long as the two population means are equal. This is under H naught under the null hypothesis. Okay? So we actually can come up with different situations. We come up with different test statistics. So for the variances known, we're going to assume a normal, Z naught is a normal 0, 1 under H naught. And here we would say that for large sample sizes, we'd say that Z naught is approximately normal 0, 1 in greater than or equal to 30. Okay? All right. And so then we would have, what if we have small sample sizes? This happens a lot. So we have two cases here. The variances are unknown. If we assume that they're equal, we're going to use the pooled sample variance. Okay? The pooled sample variance. That's what the P is for. And so we take this weighted average, if you will, of the variances, and I've got a mistake. That's supposed to be S2, and this is N2. I forgot to change them. So, yep, I have another place I forgot to change them as well. This is 2, and this is 2. Okay. So we have so we have Y1 bar minus Y2 bar, and I've put the minus 0. This can be generally written as Y1 minus Y2 in parentheses. Okay? So if you're not using 0 here, if you're not saying they're equal, if you're saying that the value is something else, then this would still be, so again, if this is mu1 minus mu2 quantity, okay, instead of 0, we're substituting for 0 there. And again, the same thing here. If we have mu1 minus mu2, if mu1, mu2 is equal to whatever value we put here, if that's true, then Z naught is still a standard normal because this minus this should be equal to 0 for the mean. Okay? So these test statistics, under the null hypothesis, these test statistics should all be near 0. So the further away they are from 0, the more likely it is that the alternative, or H1, is true. Okay? So here we're assuming, so here we don't know the variances, so all we've done is we've substituted in for S1 squared for sigma 1 squared and S2 squared for sigma 2 squared. Okay? So that works when n is large enough. Larger n is, the better that is. When n is small, we'll have to use the t-statistic. Even when it's large, you could use the t-statistic and adjust the degrees of freedom, but the differences are going to be pretty small. Okay? So that's a choice that you can make in real life. All right? So I personally use the t-statistic when I don't know the variances, which is almost all the time. That way everything is consistent. Okay, I'm getting the best answer I can. So the pooled variance, the pooled standard deviation there's no square. And then we calculate that here. And the degrees of freedom in this case are N1 plus N2 minus 2. That's N1 minus 1 plus N2 minus 1. Okay? So the degrees of freedom under the first treatment level would be N1 minus 1, and under the second treatment level would be N2 minus 1. So we combine them, we add them, we get N1 plus N2 minus 2. Now the last case is the most common case. It's where the variances are unknown and we cannot assume that they are equal. So to do this, we need to test. Perform a test. So right now, we'll just say whether or not the variances are equal or not. But in the end of the chapter, we're going to learn how to actually test whether or not they're equal. And then that will determine which one of these tests we use. Okay? And so when they are not equal and they are unknown, we will have the same quantity on the top in the numerator. But in the bottom, we're going to end up with this, the same quantity here and here, but here we did not have a degrees of freedom because these were normal. right? We had a normal 0, 1 distribution. Now, because we don't, we have to calculate our degrees of freedom, nu. This is nu, the Greek letter nu. And this degrees of freedom is called the Satterthwaite degrees of freedom, okay? Estimate of the, or adjustment for the degrees of freedom. So this is quite an involved equation. Make sure you get everything correct. So S1 squared over N1 plus S2 squared over N2, entire quantity squared in the numerator. The denominator, this plus is in between these two. So we have on the numerator in this term, S1 squared over N1, quantity squared, all over N1 minus 1. And in this term, we have S2 squared over N2, quantity squared, and then N2 minus 1. So this is quite involved at times, just tedious to get correct. So, So let's make sure that this is a 2, and this is a 2, and then our equation is correct. Okay, so those are our test statistics. All right, we'll stop at this point in the video. Please don't forget to update your formula sheet if you haven't already. If you have questions, please come to virtual office hours. If you need help before then, you can't wait, by all means, email me. I'll get back to you as soon as I possibly can. I'm happy to help you. Please take care of yourself, and we will see you next time.